Alright, hell yes. This video is all about, hey, we all know this identity, but who knew you could just do two simple things to get two more identities? So that's what we're going to do, because one of those is going to be useful to tackle the derivative of inverse tangent of x. And here's the problem that required me to use tangent, find this angle, finding the tangent, and then taking the derivative of that. Alright, hell yeah. So, what we're going to do is just this part. So, heck yeah. So on this, we're going to do, we're just going to divide both sides by sine squared theta. You know what I mean? So that's pretty sweet. And this is going to be 1. And then this one's going to be cosine squared divided by sine squared. And we just get to it. That's going to be, let's do this over here. Because we have sine divided by cosine. What does that look like? Well, that is tangent theta. So if we have cosine, and then check this out, you just flip it on itself, booyah, we get cotangent of the angle. And if we just square it, we do that. And this is the tricky thing, because, some people, it took me years to be like, what the hell is this 2 doing right there? It's the same thing as sine theta, and then just squaring it. So it's the same thing as saying sine theta times sine theta. Cool. But, so if we, I guess let's spell it out in 2 steps. So we have cosine squared theta divided by sine squared theta is equal to 1 divided by sine squared theta. Now even this, we can write it like cosine theta, and then sine theta, sine theta. And maybe make brackets around it and be like, whoa, yeah, hell yeah. That's just going to be, well, let's do this. Cosine theta, sine theta is cotangent theta. Oh, I guess I just squared it. But going back to this one, hell yeah. So this is cotangent theta and this is cotangent theta. Even though no one knows what the hell a cotangent is. But it's just the inverse tangent. Okay, I can dig. And so, hell yeah. So this just becomes 1 plus cotangent squared theta is equal to... Now, what is this? This is where, like, hey, you should always keep things in this form. Because the other one that we're going to try to solve for is 1 divided by cosine squared theta. Now, this one is going to be secant squared theta. So in general, if you have anything cosine that's 1 divided by cosine is just secant, or in this case, secant squared. And how would we do that to spell it out? Well, 1 divided by cosine is the same, 1 divided by cosine squared is the same thing as 1 divided by cosine multiplied by 1 divided by cosine. Cool. And so what did we say 1 divided by cosine was? Well, that's going to be secant. And then this is going to be secant. And heck yeah, we're going to have secant squared theta. But for this, we have sine. So what is 1 divided by sine? No one knows, but it's cosecant. It's really even difficult to spell. Sweet. And we're going to have 2 of those. So let's spell it out. We're going to have 1 sine theta, 1 divided by sine theta. So this thing is going to be cosecant theta times cosecant theta. And we're going to have cosecant squared of theta, which is just, that's the same thing as cosecant theta brackets squared. This is the same as this, is the same as this. And the identity for this, well, we don't have much room, is 1 plus cotangent squared theta, because we got 2 of them, is equal to cosecant squared theta. Now, hell yeah. So if I ever run into any trigonomic problems that involve cotangent squared, I can be like, whoa, I can just replace it with this. And then just know that, hey, that's going to be, this is 1 divided by sine squared theta, and I'm not going to lose my mind. Alright, so we're going to do the other one that's actually useful to this problem, and then we'll solve that problem. Alright, booyah. So now we can kind of go a little bit faster, but we're going to divide by cosine squared theta on both sides. Now again, we can do this because it's wait, oh, this is fast, and let's slow down, because sometimes you're like, well, why can we do that? It's because like the equation's balanced, it doesn't change the equation. But how do you, like, is it like multiplying by 1? And this blew my mind. It's like, hey, let's just take everything to one side of the equation. So we're gonna go like, hey, 0 is equal to sine squared theta plus cosine squared theta minus 1. And hell yeah. And I don't even know what I'm doing right now. Alright, hell yeah, scratch that. So we'll just move on. So we're going to have sine squared divided by cosine. Now, can we just do this in our head? Because sine divided by cosine is tangent. We're going to have two of them. So you can just instantly see that's tangent squared theta. This is plus 1. And then this is 1 divided by cosine squared theta, which is secant squared theta. And I guess my brother was saying, hey, how do you know how to convert, like, does cosine go to secant? Sure, because you have COS, and you're kind of like flipping it, and you're going to have an SOC. And I don't know. You know, it's not the best, you know, because you can probably, you know, I don't know. If you flip sine, you don't get anything. And if you flip cosecant, you're not going to get anything. So secant is the only one where if you spell it, and you flip it, you get something. You know what I mean? So I don't know. And you're going to get cosine. So that might be a decent way. Okay, hell yeah. So now let's tackle this problem for the first time because it sucks. And then we're going to actually use it in this problem. So let's do that. Alright, hell yeah. So this one's tricky. And I think it's even tricky because this stands alone. You know, where someone's just like, hey, find the derivative of this. But then, like, let's kind of, you know, draw our little triangle and be like, what does this even mean? You know, so I always draw like a 30-degree triangle. But I'm going to have, you know, theta here. I'm just going to call it 30 degrees. And then I just say 0.5 and 0.866. This is a really good one to know. Cosine 30 is pretty much, you know, it's almost 100%. Cosine 30. Let's get into degrees. Alright, yeah, it's 0.866025. So it's just, you know, those three digits are just 100% accurate, basically. And now we need to know. So let's just write. Yeah. Let's do that. Well, I don't know. Let's just write tangent of the angle, and that's going to be opposite over adjacent, so 0.5 divided by 0.866. And hell yeah. But let's say we didn't know the angle. How would we find the angle in our calculator? Well, we would actually take, like, we would say theta is equal to, and maybe I just know this and I'm actually not going through all the steps. Like, I always think there's some hocus pocus going on. But let's write this again because there's not. Like, I think that's the most important thing with math is to make sure nothing feels like hocus pocus. Everything feels like, you know, legitimate steps. Because here, to unleash this theta, we take the inverse tangent of this. We take the inverse tangent of both sides. Sweet. And then so that pops out that theta is equal to inverse tangent of 0.5, 0.866. And now let's do the same thing. Let's say I want to, well, you can't do the same thing. What we would need to do here is, if this is the inverse tangent, we would have to take the tangent of this. If we take the tangent of both sides, those are going to be equal. And then we would have tangent theta. I was going to make a big mistake there. 0.5 divided by 0.866. But even that, I don't know. It's just because there's nothing special like cool. When you say the tangent of this angle, I'm just going to say that's 0.5 divided by 0.866. And before I even do it, it's basically like 0.5 divided by 1. It sounds like it's going to be... Wait, 0.5 divided, a smaller number divided by a bigger number. It's going to be like 0.5. It could be a little bit bigger. Maybe it's like 0.6. Yeah, it's like 0.577. Okay, now what? You know what I mean? Cool. That was the tangent of this angle was going to be 0.577. Like, I don't care, you know. But this angle is... yeah, I guess we can kind of slow down. It was fascinating to me that if you have a right triangle, all you need to know is like two things about it. I think, yeah, literally, that's pretty wild. Because there's a lot going on. You have three sides and an angle, right? You almost have three sides and this angle and that angle, and this is 90 degrees. But is that true? I only need to know two sides to know everything about it. And it's not quite true. You do need to know it's a 90 degree or right triangle, and so that does give this angle up. But in general, you know what I mean? I don't know, it's just kind of fascinating. But if you know both these sides, and you put them at right triangles, you can only connect this line, and this angle has to appear. You know what I mean? So with this, and tangent, you know, of whatever angle you're trying to find. But if I just say, hey, the tangent is this number. So now let's just say, hey, tangent is a number. What is that number? It's the ratio between, like, hey, this side that we call the opposite over the side that we call the adjacent. Now, the bummer about tangent, and I think it's just a little bit trickier, is... yeah, so we're definitely going to slow. This is kind of where I wanted to take the video. It's like there's no reason to do differentiation. Like I got to stop doing differentiation without even just kind of trial and error. You know what I mean? Because you even forget what the d means and then what this dx means. You know, and it's maddening. So we're going to cover it. Hell yeah. So yeah, it's just the ratio. So I guess I thought the cool thing to do for this is draw a 30-degree triangle. And then we're going to draw a 45-degree triangle. Then we're going to draw a 60-degree triangle. Alright, hell yeah, maybe like that. 60-degree. And I think we're good. And, you know, and so I know this is 0.5, 0.866, and you should just get used to it. You should at least know these. And hell yeah, this is 0.5 and 0.866. So we have a... This is 30 degrees, 45 degrees, 60 degrees. And this is 0.707. I just think 007, and obviously you're not going to do that. And obviously, I don't know, 007. I guess it's two sevens, which is hella confusing. But you wouldn't do 770, else you just call it two sevens. And so, I don't know, 007, I can just remember that. That's a good one to remember. And, alright, sweet. Oh yeah, so we were trying to find the ratio. So this tangent is kind of, hey, knowing the ratio between these two numbers. So again, we said, hey, this is close to 0.5, like 1, you know, just guess, like 0.5 divided by 1, that sounds like 0.5, but it's like 0.6. And, you know, the more you guess, you'd be like, hey, it's 0.6, but then it's like, or I guess if I was guessing this, I'd be like, hell yeah, it's 0.5, who cares? Else it's 0.6, get a little bit better, or it's 0.577 because I kind of memorized the number. I think that is a very good thing to get in your mind. Just be like, who cares? Guess a little bit better, you know, and then maybe memorize. And yeah, so this, at the end of the day, this is just 70%, a 45-degree triangle. And what does that mean? It means that if this is, I don't know, like 10 inches long, this is 7 inches. This is 7 inches. You know, if this is 1 inch long, hell yeah, this is 0.7. And same thing here. So, like if this, usually you do right triangles like 1 or 10 or 100, doesn't really matter. But if this is a length of 1, hey, look at this. Cut it in half and be like, oh yeah, I see it. I see that this length is about that length. See that? And so same thing over here. This is my hypotenuse. This is kind of the driver of a triangle. And you're like, hey, what is this length? Well, this length is about half the hypotenuse. And when your hypotenuse is 1, the numbers on these represent the percentage. So this is 50% of the hypotenuse. This is 0.866 of the hypotenuse. When the hypotenuse is 1, you get this nice little decimal. Now, if this was like 5, well, then this would be half, or 2.5, and this would be about 90%, 85% of 5, maybe like 3.7. I don't know, 0.866 times 5. I'm just going to re-guess and say 0.42. 0.43. Alright, so guessing skills are pretty good. Alright, so and then the ratio here. Tangent was opposite over adjacent. That's going to be a ratio of 1. So hell yeah. And then this is going to be 0.866 divided by 0.5. The initial guess is, especially on this one, hey, just guess 1. Because look at this. Look at that length. It's about 1. Look at this length. Isn't that about the same? Like just, you know, if you do a quick guesstimate, hey, these two lengths are about the same, call it the same. 1 divided by 0.5, hey, we're dividing by a smaller number, so it's 2. You know what I mean? So this one's 2, but if I do it for real, 0.6, so 1 divided by 0.5 is 2, but 0.866 divided by 0.5, well, this is a smaller number compared to that number, so my number is going to be less than 5, maybe 1.7. Cool. And if we do 0.866 divided by 0.5, yeah, we get, whoops. Yeah, we get 1.7. Hell yeah. And so, perfect. So we just found the ratios. We just figured out what tangent was. You know what I mean? Hey, we get a number for the ratio for tangent. But I guess this is really good because, you know, man, until recently I'm just like, oh yeah, no duh. If I just know like a couple things about this triangle, I kind of know everything about it. If I just knew the hypotenuse and this length, I know everything about it. As long as I know it's a right triangle. And yeah, sure, that's like 3 things, this, and that. But still, it just feels like just knowing 2 things, you know everything about this triangle. And that's kind of cool. And so we use that to our, you know, we just know that. So if we know these 2 sides of a right triangle, we know everything about it. And we know, yeah, we know the angle. And but the bummer thing is given this number and given this number, there's no polynomial equation. There is a series that we could use. And let me go look that up right now, because that'd be very fascinating. Alright, hell yeah. So here's a page of series. Now this is Eschbach. This is Handbook of Fundamental Engineering Fundamentals. And so, for sure, so we do have inverse tangent of x. And now this has to be in radians, you know, so we got pi divided by 2 minus 1 divided by x plus 1 divided by 3x cubed minus 1 divided by 5x to the 5th. Okay, sweet. So yes, so there is, that's the bummer, is there's just no nice simple polynomial. It's a series expansion, but I mean, you could say the polynomial, like this, might be good enough. This might have like a 5% error, maybe less, maybe 1% to 5% error, and this has a, you know, and then, you know, so that ain't too bad. Okay, so but we have to, the only thing, because when we do this equation and we take the derivative of inverse tangent, you know, the answer is 1 divided by 1 plus x squared. And this, let's see, this x is that x. Cool. Oh man, am I messing this up? Oh yeah, just like back to even like what is, well, we're getting closer to like, hey, what is, like, hey, I forget the derivative, like what is the inverse of x, you know? And so we have shown that, and sometimes this gets confusing because you might have sine of x, and isn't x an angle? See how x is an angle here, and inverse tangent, well, that's going to be a ratio, because didn't we say like, hey, this is an angle, and didn't we say if we have tangent of the angle, that's going to be equal to x? You know, so this x in both of these two equations hasn't changed. It's still the ratio. It's still 0.5 divided by 0.866 using a 30-degree triangle. But when we take sine of x in all of like the books and the literature, this is an angle, and typically people work in radians. Okay, so but that was just like, hey, so this x is a ratio and this x is a ratio. So I just thought it would be kind of interesting to even just write the words in. So we have sine of an angle, you know, and that's where if you're taking, you know, sine of x, if you're saying this is an angle, I don't know, it's definitely very useful to just say, hey, sine of theta, because theta is classically used for angles. I've never seen any physics problem use theta for like the position in Cartesian coordinates. You know what I mean? Like, hey, I'm going from 0 to theta. Oh, the grocery store's theta miles away. You know what I mean? So hell yeah. And okay, so there's a few things about this problem. It's like, one, we need to know what the hell triangles is. We need to know what the tangent is. And so we got that far. We know the tangent of the angle is that ratio. And it's this divided by that. So we have that. We can even say just tangent of the angle is equal to a number. We can even say tangent of the angle is equal to x. And so yeah, so that's kind of where we're at. Sure, yeah, and we're trying to figure out, but we do need to know what these angles are in radians. So I always say, you know, if we're going to do radians, I always say, well, I mean, I don't know. If you can remember 60 degrees is 1 radian, that's pretty sweet. A circle has 2 pi radians, but there's basically 6 radians in a circle. So, you know, anytime you're thinking radians, take a circle, divvy it up into 6, and be like, hell yeah, that's a radian. And I guess you should probably even simpler, draw a circle in a radius, and even start here to be like, what's a radian? Because if you take this radius, cut a string, and then drape it around the circle, you'll get to about there. And so hell yeah. And this might look like 45. It's definitely not 30, but it's about 60 degrees. It's 57 degrees. Cool. But basically 60. And there's going to be 6 of them in a circle. Okay, so, but again, hell yeah. So I was doing 90 and then kind of divvy it up into 3. So there you go. So this is going to be 1 radian. 60 degrees. So if 60 degrees is 1 radian, you know, classically the 30-degree triangle is 0.5 radians. So, and it's an angle, you know, so it's still angle in radians. And so now we can kind of go in and do all these. So if this is 0.5 radians, this is, I'll just double box it. This is going to be double that. This is going to be 1 radian. And if 45 is halfway in between, well, it must be like 0.75 radians. And obviously there's going to be a little discrepancy, but this is the best way to go. And let's even draw another triangle that's only has 0.25, not 0.5, and then we're going to go out here. So this angle we're just going to say is about 15 degrees. And this is kind of a true statement. You know, if we halved 0.866, we would get like 0.433. Now, that's not close to 5, but once you get to a 30-degree triangle, hell yeah, you can just half it, and it's basically 15 degrees. You could do it again and say, hey, this is 0.125 in height, and now this is a 7.5-degree triangle. And so the same thing with radians. If I know this is a half a radian, at 30 degrees, a quarter radian is 15 degrees. And 0.125 radian is 7.5 degrees. So there you go. So I know, and this is very useful when doing trigonometry problems. And I was even in my notes, I was even like, well, we could go the other way. You know, you can chop this in half, and so we're going to go 0.25 here. This is going to be 1. And now this gets even, you can just literally call it 1. It's like 0.94 at this point. And what's the angle here? Aren't we halfway between 60 and 90? So isn't this going to be like 75 degrees? And so, so booyah, we got about 75 degrees. And, so what's 90? If 30 is a half a radian, 60 is 1 radian. You know, if we just have 90 degrees, that's going to be 1.5 radians. So if we're halfway between 1 radian and 1.5 at 75 degrees, we're going to be 1.25 radians. Okay, hell yeah, and I think we're done. You know, you could obviously keep going. You know, you could go halfway between 1.25 and 1.5. Maybe that's like 1.38. You know what I mean? But anyway, so I think we're done here, because now we're going to use these values to actually, you know, throw them in here and be like, yeah, well, let's figure out what this derivative is and what it actually means. Alright, hell yeah. So now we get into the hocus pocus, but hopefully we're going to shed some light on it, because we need to take, so again, the tangent of whatever these angles are just the ratio between these two numbers. Oh, so we have a few more to do. So this is almost 1 divided by half. This is close to 2. We already did that. Now if we go from 60 to 75, this is going to be 1 divided by 0.25. So hell yeah, this ratio is going to be 4. And you can just go up to the next. If this was only 75 degrees, let's do this. Let's go 75 plus 90 divided by 2. If we go up to 82.5, the ratio is going to be 0.125 and 1. You know, this length basically becomes 1, like 0.999, very fast. That's why even right here is a really cool trick you can do, is just to associate this with 1. But now we have a ratio of 1 divided by an eighth. You know, 1 divided by 1.25. 1 divided by an eighth is the same thing as 8. 1 times 8. So this is going to be a ratio of 8. And you can see as we approach 90, this thing is going to, you know, double every time. If we get halfway closer, this thing's going to double. So the next is going to be 16, and then so on. I will say, though, especially working with tangent, is like whoever heard of a tenth of an angle, you know what I mean? Like even in like machining, I don't know. It's just like even the human eye, I just say, hey, just focus on, just think that 1 degree of an angle is, whether it's 89 degrees, you know what I mean? Hell, that's 89 degrees and this is 1 degree. So, but just, especially when you're working with things that will just go to infinity, if you start moving from 89 degrees to 90, or 0 to 1, or 1 to 0, you know, so if you just stick within like, so yeah, if we get this to 1 degree, this ratio is only going to be about 60. It's going to be 57. You know, it's going to be that, anyway, you know, that number 57 comes up quite a bit. One is this, anyway, I don't know if it's 100% just because a radian is 57 degrees. That's probably something to it. But just know that, hey, instead of that number going to infinity and making things seem nonsensical, hey, it just goes up to about 60, call it good. So we're going from 0 to 60 instead of 0 to infinity, you know what I mean? Alright, but now the hocus pocus. So we're going to have inverse tangent. So inverse tangent of 1, you know. This is going to generate that angle of 45 degrees. It's going to generate this angle of 0.75 radians or 45 degrees. So when you throw in inverse tangent of 1 into your calculator, it's just like, cool, I've already stored that knowledge and I just know. So it's a this for that. Let's do this one. Inverse tangent of 0.5. Inverse tangent of 0.6. Inverse tangent of 0.577. Well, it's just going to spit out 30 degrees. You know, if your calculator is set to degrees, it's going to spit out 30. If you do inverse tangent of 0.577, it's going to spit out 0.5 radians. And there's also called tangent also, like literally we already went over it, that tangent of an angle is sine theta divided by cosine theta. And with really small numbers, this just really rapidly, 0.999, really rapidly approaches 1. This value. And then this gets consistent. So just like we were saying, so what's going to happen is inverse tangent of, let's do this, inverse tangent of 0.25. Well, we just know that's going to be 0.25 because, why do we know that? Oh man, this is tricky. I wish I had some more paper. Let's get some more paper. Alright, hell yeah. Is because, yeah, and this is, so if we have inverse tangent of x, what does that even mean? Or what does this give you? Well, it gives you the angle. And then so you can, again, not take the inverse tangent on both sides. You have to take the tangent. I mean, even though this is just like, hey, I'm spitting in an input and I'm retrieving an output. Your calculator, and we're going to get to it in a sec, is doing this equation and then just saying close enough. But instead of us doing this equation, we're just saying, hey, it's just a this for that. Alright, but it's cool because that sine, the sine function from 30 to 0 is, is linear. And if we know that 30 is 0.5 radians, well, 15 degrees is going to be 0.25 radians. So let's take the tangent of both sides. That's going to give us, I'm just going to flip them around. We're going to get tangent of the angle is that ratio. And so, so what are we saying? We're saying, hey, I know this angle. Let's just do it. So tangent of 0.25, we know this ratio is going to be, yeah, we know the ratio is going to be 0.25. And that's going to be this divided by this. This basically becomes 1. Hypotenuse is 1. And this basically becomes the same length as the hypotenuse. So it's going to be 0.25 divided by 1. And hell yeah. And so I guess I don't know why I'm confusing myself. Tangent theta is the same thing as sine theta divided by cosine theta. Yeah, and because this is a ratio, that's the other thing. Let's draw this. Because if I have a right triangle, this 30-degree triangle, and instead of writing 5 right here, this is probably better for your knowledge. Write 50, and then, or write even 500. Write 500 and then 866. So here's a triangle that's this dimensions, and this dimension is 1,000. And so you can just say, hey, if this visually is 1,000, chop it in half. This is 500. Oh, that's about the same length there. And then if we go 1, 2, 3, so it's going to be 5,000, 6, 7, 8. Let's just figure out where this is. You roll this in, and you're like, whoa, this is about 900. Well, it's 866. Okay, and so if we do have this angle in 30, let's work in degrees just for a sec. And we say, what is sine of this angle? Sine of this angle, from 8th grade is opposite over hypotenuse. That's going to be 500 divided by 1,000, and that's going to be 0.5. Oh, cool. So because it's a ratio, and let's do cosine. Cosine theta is adjacent over hypotenuse. 866 over 1,000, and that's 0.866. And this is cool because the take-home point for any application of a right triangle, especially from physics or just anything, is typically we know the hypotenuse. We basically, this is your vector, this is the distance you're going at that angle, for some time. You always know this vector, but then the vector is always at some sort of angle, and you're not measuring. You're always kind of measuring maybe in Cartesian coordinates, whether it's going to be up in the sky and over across the ground. You want to know how high something got and then how far it got this way. And so, but let's say, in a lot of physical applications, this distance. You know this magnitude. I'm putting a 1,000-pound force in that direction on something. On this wall. Cool. And I know this wall is only stuck in the ground. Just actually pretty. I don't know, kind of shallow. And I'm worried that this thing is the force is going to pull up out of this ground. Or maybe, hey, maybe this wall can only take 1,000, maybe this wall can only take 900 pounds of force when you push on it this way. So now if we're putting this 1,000 in, now what? You know what I mean? Well, it's got two components, a component this way and a component this way. So this component, it's going to be half. So if you were worried about this coming out of the ground, maybe you should, because half of this load is going to be pulling this thing straight up. And then we have 866 pounds, pushing into the wall. It's not pushing in right here. These are just the components. It's just kind of how we draw it. You can draw it as a parallelogram and go either way, up this way, the Cartesian coordinates. But hell yeah. And so the other thing to look at is so we have a 1,000-pound force. These components are always going to be less. And I don't know, that was just kind of a mind-opening moment, that these two components are always going to be less than this. Or equal to, I should say that, or equal to, or zero. But, I mean, if there is some sort of angle, usually there is. If there wasn't any angle, we wouldn't have a question. You'd be like, okay, we have 1,000 pounds that way. What the hell are you even talking about? Obviously there's 0 pounds up. So in the realm of hey, we do have this little triangle. What about it? These are not only smaller. That's kind of the first. The second is that they're percentages of this hypotenuse. And even the drawn the way it is, you can see that this distance is half, or this distance, if you half it, is the same as this distance. So you can say that this is 50% of whatever this is. So this is 500 pounds. So visually it represents, and that's very useful. And I don't even know why. Is that just a law of physics? Just a law of the universe? But hell yeah. So, but yeah, that is what it is. If you're this, that's actually a principle probably just of the universe. If you're pushing in this direction, you are pushing in this direction and pushing this direction in these amounts, because they are additive. It's there's no difference between pushing this way and then pushing this way. It's kind of, it's bizarre. It's I don't even know what the proof on that is. I take that for granted for sure. But anyway, so visually, this is a percentage. This is 86.6% of this, and we have 866 pounds. And then also in your calculator, okay, yeah, there's a couple things going on. One, we can just draw this graphically and we can measure it and be like, yes, this is 50% of that, we're done. The other thing about this, though, is that we can also measure this angle out of a 360 degrees and then call it 30 degrees. And then we can just say, it so. We say that, yeah, it's bizarre. It's like we only need to know two things about this triangle, and we just have four ratios. Oh, this is fascinating to me. We just have two ratios that involve the hypotenuse, which are the easiest to understand and make sense of. We can either take 50 divided by 1,000, and we can call that sine, or we can take 500 divided by 1,000, or we can take 866 divided by 1,000 and call that cosine. Now I'm going to blow my mind too, because like you wouldn't have had to, if you wanted to really, if the mathematicians really wanted to play a joke on us, they could have done it the opposite way. There's no reason that sine of 30 couldn't be hypotenuse divided by opposite. You know what I mean? So then you would have 1,000 divided by 500, and you would have 2. It's just, that would suck, because then this number doesn't really represent, like the opposite of this number actually represents something useful. This number really doesn't what it represents, it does. No, hold the phone. This number would represent that the hypotenuse is double the opposite. So it would be the ratio of like, hey, how many more times, like x hypotenuse, how many more times, or like x number, how many more times is the hypotenuse compared to the opposite? That's what that would say. And if our calculators did that and spit that out, we would just have to go with it and be like, okay, this sucks. Well, it all sucks. But yeah, this is fascinating to me. But it's just because they say so. Sine of 30 is opposite over hypotenuse. But a cool thing happens here. Because if we type in our calculator, sine 30, and we get 0.5, multiply by 100, in any because it's a ratio, and we already said 500 divided by 1,000 is 0.5, and you can treat this as a ratio between 0 to 1, and you can treat this as a percentage. It's a percentage of the hypotenuse, and so that is very useful. So if cosine 30 says 0.866, I know that 86.6% of this 1,000 is in this direction, and I can just go on with life. Oh, hell yeah. And I just did my first cosecant. There you go. Because I just said it could have been the opposite. We actually have... I'm surprised even this TI-84 doesn't even have cosecant buttons. Like, no one uses cosecant. No one uses secant. It's the worst. It makes trigonometry just like, what are you doing now? But all it is just taking the opposite of these. And we just did our first one where we saw the significance of that. If we took the secant of 30, so that would be secant of 30, it's going to chisel us out the inverse of sine 30. It's going to take sine 30 and take the inverse of it. That's going to be 0.5 inverse. That's going to be 1 divided by 0.5. That's going to be 1 divided by a half. That's going to be 1 multiplied by 2 divided by 1. It's going to be 2. You know what I mean? And what that's going to say is the hypotenuse is twice the opposite. So that's going to say, hey, whatever your opposite was that you put in, or if you know your opposite, your hypotenuse is going to be twice that. Interesting. Alright, hell yeah. Alright, hell yeah. So let's draw our 30-degree triangle again, because we're trying to understand what inverse tangent is, and we're first going to learn what inverse sine is and inverse cosine. So we have our 30 degrees. We know this is 0.5, this is 1, this is 0.866. Now, again, if you're not... This one I like, for this is a unit triangle. Obviously, we made it 1,000 and 500 and 866, but making this one, I don't know, I just like it. And we can do sine of 30. So let's do sine of 30. What's that going to chisel us out? Well, that's going to chisel us out that 0.5, because it's 50%, because it's the opposite over the hypotenuse. Yeah, and that's so... Definitionally, I just think sine 30 is the percentage of the vector of the hypotenuse, the larger number. It's the percentage of that, typically in the vertical direction, but just the opposite direction. I do sun is shining on the sinin. So this is going to be the sine component. If you did your triangle upside down, where if you said this was 30, this is the sun is shining, this is the sine component. So you could, or that would be like, hey, this is 60 degrees. So if we took sine of 60, well, that's going to be this. The sun is shining on the sinin. Okay, hell yeah. And what does sine of an angle mean? It's the percentage in that sunshine and direction, so that opposite direction. So of the hypotenuse, it's the percent. So this is 86.6% of the hypotenuse. Cool. Okay, so now what we're going to try to, and so that's going to chisel us out this number of 0.5. So now we can say, hey, what is the inverse sine of 0.5? Well, what this says is this is still the ratio. So if we have inverse sine of we're talking about the opposite, maybe the vertical component, the opposite, vertical, sun is shining. But when that component, when the sine component is 50%, that's kind of what you're reading. When it's 50% of the hypotenuse, what type of triangle do you get? Is it a 30-degree triangle? Is it a 60-degree triangle? And so hell yeah, it's a 30-degree triangle. And so now let's do one. Let's do inverse sine of 0.707. Okay. So the vertical component's going to be 0.707. This component must be 0.707. Hypotenuse is 1. And that's going to give a 45-degree angle. Cool. And now let's even challenge ourselves. Sine of 0.25. We did. So that's going to be 25%. We did that 30-degree, and this was 0.5, so maybe it's a 15-degree triangle. Hell yeah. And let's also, and this is the crazy thing about trigonometry, so inverse sine of 0.5, do it in radians. Well, I don't know what 30 degrees is, but I do know 60 degrees is 1 radian, and you should try to memorize that 30 degrees is 0.5. That should just pop into your head. Now, it's not exact. If we go to radians and we go sine of 30, we're going to, inverse sine of 0.5, we're going to get 0.523 radians. Hell yeah. And yeah, and this is where working in radians sucks, because you're just like, wait, aren't these numbers the same? It's like, no, again, this is the ratio. And for sines and cosines, it's really easy, because it's just the percentage of hypotenuse, percentage of that total vector. When it comes to tangent, it's the ratio between the opposite over the adjacent. It's just this ratio, which can go from 0 to 60, or infinity. But like we said, 0 to 60 is a good frame of reference. And even for small angles, we went 0 to 8, even 0 to 4. So you can think, for all practical purposes, in this inverse tangent, 0 to 4, what would that mean? No, tangent of most angles is going to be some number between 0 and 4. 0 to 32, 0 to 60, for sure 0 to 60, and even, yeah, so let's even do that. What's all right, I'm going to ask my first question. The question is, if the tangent of an angle is 4, what does that mean? And then how can we go about finding the angle? From mathematics, I can just say, hey, let's find the inverse tangent of this and take the inverse tangent of this. And this is where my mind kind of melts, because I'm so used to doing inverse sine to get the angle and inverse cosine. And when we do, so let's go back to that, because inverse sine and inverse cosine are this percentage of hypotenuse. You know what I mean? And that percentage is always going to be a number between 0 to 1. Inverse sine, let's go back to degrees. Oh, it doesn't matter. Oh, that's the other thing. Whether you're in radians, whether this is 0.5 radians, this ratio is still the same. So let's not do things that are counterproductive. But we're still going to be in radians, and we can go inverse sine of 0.5. That's going to give us an angle of 30, or 0.5 or 0.523 radians. Sweet. And if we do cosine, if we do inverse cosine of 0.866, we're going to get that, again, that's going to be that same angle. And then if we do inverse sine of 0, it's not going to blow up. And inverse sine of 1, it's still not going to blow up. What would inverse sine of 1 be? Inverse sine means that the opposite is 1. The hypotenuse is 1. And then this, the adjacent is 0. And so we're going to have an angle of 90 degrees. 90 degrees, and an angle of 90 out of 2 pi. So this is going to be pi. This is going to be pi divided by 2. So this is 3.14. Always good to divide. Hey, what's 3.14 divided by 2? I don't know. What's 3 divided by 2? 1.5. Okay, what's 14 divided by 2? 0.07. Cool, 1.57. So that one's pretty decent to memorize, that 90 degrees is 1.57 radians. All right, or just 1.5 and call it a day. All right, sweet. So I was just pointing out that anytime you do sines and cosines, it's always going to be 0 to 1. It's always going to be a fraction. But if you do inverse tangent, hell no, sky's the limit. You could go 0, you could go to 57, 60. That's kind of the top end, I would say. You can't go negative. You can't go negative 0.1. Let's just do that. Inverse tangent negative 0.1. Or maybe you can. Ah, damn it. Oh, yeah. Yep. Because this triangle, this is wicked. That's why I hate the unit circle. Hey, we're just doing this 30-degree triangle right here. We could easily take this triangle to this side, and that means that the ratio is going to be a positive number divided by a negative number. And hell yeah. So it's still going to be a ratio between... so inverse tangent can be a ratio between negative infinity to infinity. All right, sweet. But that's where I kind of draw the limit. I like to just work on this side of the circle. There are problems where it's just like, nah, let's say this. If you always start here with your angle, like, hey, this is 30 degrees or 0.5 radians or 30 degrees. Hey, what's this angle? Well, if we said it was 30 degrees over here, this would be 60, so it would be 90 plus 60. That's 150. Sweet. So if you take all your angles from this baseline and you say sine of 150, that is going to be still the vertical component. It's going to give you a positive number. It's going to be a positive, and this is 1. This is going to be positive 0.5. But if you do cosine of 150, that's the adjacent over here. And this is positive, this is positive x, this is positive. So it's going to be negative. It's going to be negative 0.866. So sweet. So we're going to have cosine 150. Got to get to degrees. Negative 0.866. All right, hell yeah. All right, back to my question. If I have tangent, what did I say? If I had inverse tangent of 4, what angle am I going to chisel out? Because this would be the same thing as saying, hey, tangent of whatever angle that is equal to 4, so that ratio. So let's just start drawing some triangles. You know, hey, is this... Hey, look at this. This looks like 1, and this looks like 1 and 1. So this ratio is 1 divided by 2. That's 0.5. Okay, so we're going the wrong... I was even thinking about going this direction. Like this is 1 and this is 4. 1, 2, 3, 4. That would be 1 divided by 4. That'd be 0.25. Hey, we're going the wrong direction. So now let's get our angle to where this is 4 and this is 1. Opposite over adjacent. Okay, hell yeah. So now let's actually represent that out. We got 1, 2, 3, 4, and then we're going to go over 1. All right, sweet. So that is our angle right there. And if we go, hey, that's 90, we're going to do a third. So that's 60. So 30, 60, about halfway. So 75. So sweet. So I think the angle associated with inverse tangent of 4, and that's exactly how you write it. If you have inverse tangent of the 4, you have the ratio here. So you have the ratio, that number, ratio, and I'm going to do something to it to chisel out the angle. I'm taking the ratio and I want the angle, and we use this operation called inverse tangent, you know. So now we're going to be like, well, forget that. That seems like hocus pocus. Let's actually use this. Oh, hold up. Because we're going to be, my calculator's in radians, because this thing's going to give us radians, and we have to get used to working in radians. What did we say? 60 degrees is about a radian, and we said this was about 1.5. So looks like we're going to have like 1.25. I'm going to say just a little bit more. I'm going to guess between 1.25 and 1.3. So now we're going to go inverse tangent of 4. No, hold the phone. Yeah, perfect. That's all I wanted to do right there is just guess. So now I'm going to guess 1.3 is our radians. That's how many radians we have. About 75 degrees. Hopefully I did that right. And now we're going to use this equation. Pi divided by 2, we just did that. That's going to be 3.14 divided by 2. That's going to be 1.57. Sweet, and now we minus. And the cool thing about these series, you can just do the first one. You know, so what was, and this is the ratio. You know, so this, I really want to write it again where I actually just spell the word ratio in all these. But I'm not going to do that. Like, this is the ratio. So we've covered that a million times. Hell yeah. Okay, and this is where just like, I have the aha moment just talking through this. And I don't know. So hopefully we're doing good here. So we have 1 divided by that ratio. What did we say that ratio was? Oh, it was 4. So that was the ratio. So that's 1.57 divided by 1/4. I mean, already it's like that makes total sense. It seems like we're just right in that ballpark. So 25 plus 7 is going to be 0.32. So we got 1.32. Holy hell. You know what I mean? So my guess of 1. And I swear I have not done this one before. You know what I mean? Hell no. I'll like these triangles I was kind of working out tonight, and I've done this before. Like, you should do this every time. Any trigonometry problem, at least do the 30, 45, 60, and then do 1 on either side, at least, because then you can, I mean, we haven't even got to changing this, you know? Like, what this means is like, hey, we're going to change that ratio, this is the change in the angle. Like, literally, you're changing the angle. Oh, but you also changing the ratio. So what's the angle change? Divided by the ratio change, and that's going to be the derivative. And who cares what that is? But when you do problems like this, they want that, and it's the only way to actually get the answer. So, I mean, that's the hocus pocus. Like, I can get the logic, but then sometimes when you're putting everything together, you're just like, man, I'm just going from one step to another, and it seems magical, but whatever. That's why even with this problem, I would never solve it with derivatives to start with, because I would mess up. You need to get an idea of, and we've done this problem like 3 times with other videos. Get an idea of where this thing is going, what the velocity is, what the acceleration is, and then you can, you know, work through hand derivatives and get really cool equations. Okay, hell yeah, let's focus. But I think we did this one. And so now let's do it for real. Pi divided by 2 minus, I'm just going to do 4 stored as x. So pi divided by 2 minus 1 divided by x, and we get 1.32. We're going to add 1 divided by 3 divided by x cubed. That's going to be 1.3. So like this hardly improves. We went from this to 1.326. And now let's just throw it into our calculator. Inverse tangent of 4, the actual answer is 1.3258. So this is closer, you know, and then we'd also subtract. So, yeah, this is really cool. And let's get the error right off the bat. So stuff like this is just like, well, what is the error? I don't know, just guess. Like, if if this equation chiseled out like 0.7 and the actual answer is 1.3, well, the error would be 50%. Okay, so, so then, I don't know, you see how you can do that pretty easily? 0.7, 0.8, so honestly, like 1.2 might be, if the answer is like 1.3 and this gave you a 1.2, off the first two digits, yeah, it might only be 90%, like 90 to 95. The first digits, hella off. So how do you do, percent error is not too bad. I think you're not going to mess it up a whole lot. We're going to go inverse tangent of 4. We're going to store that as alpha A. So we're going to take that number, 1.3258, add it. What are we going to do? Actually, we're going to subtract it. So we're going to subtract pi divided by 2, this first number that we got. And, I don't know, you're going to take the absolute value, don't freak out. But then you're going to divide it by the actual answer. And so we're going to take inverse tangent, or just divided by alpha A. And then multiply by 100%. So that has an 18% error. Sweet. And let's see, does that make sense? Because let's say we took pi divided by 2 minus this number, and then we took this number and then subtracted that, and then we divided it by that number, and then multiplied by 100. Just a lot of different ways, So, yeah, that would have been 80. So you're 81% close. You're not 100% there, you're 81% there. So it's kind of two different ways to say the same thing. But even just these two, it's kind of fascinating. Now, these equations, like what is this? Because our angle is like 75 degrees, I haven't even figured out what it is. Inverse tangent of 4, this is our angle. And let's do this one, because a lot of people aren't very good at it. Alright, so we've been talking that our angle that we got is like 1.3 radians. And, mentally, you should be like, well, 1 radian is 60 degrees. 90 is like 1.5. And so, cool, it's somewhere in between. Call it 75. So I would do that way first before doing the equation. Because even just right there, you can get there faster mentally. It's a good guess, and it really helps you. Now, we need to know this, factor label just says, hey, I just want to change the units. And we know that a circle, we've already said, is like 2 pi radians. Just because this radius, if you drape it around the circle, you get to there. And you can do that 6.28 times. Cool. And that's going to be equivalent to a 360 degree circle. So those two things are equivalent, 360 degrees and doing this angle 6.28 times. So that's, and anytime you're doing things that are equal, I would always stack them. So I'm going to do 360 degrees divided by 2 pi radians. And then I would write it again, 2 pi radians divided by 360 degrees. And, you could write this 4 or 5 ways just to get used to it. You could also write it as 6.28 radians divided by 360 degrees. 360 degrees divided by 6.28 radians. Just so you can kind of see the numbers involved. You could also write it as 180 degrees divided by 3.14 radians, or 180 degrees divided by pi radians, and then flip those two around. And that's all that's saying is like, hey, if I just take a half a circle, I know that's 180 degrees, and if I take this radius, I can drape it there, I can drape it there, and I can drape it there, plus 0.14 extra, and and that's how many radians. You know, that's our definition of a radian. Taking the radius and draping around the circle, and that angle that it plays out is what we call 1 radian. All right, hell yeah. But I don't know. This messed with me in college, where it's just like no one just, you know, did exactly what I just did there. Just have 100,000 different ways to do it, and then challenge yourself. You know, say that 90 degrees is pi divided by 2 radians, and use that as your factor label. The fact that you can throw anything here as your factor label, but let's just do it. We'll do 2 pi radians. But sometimes I do this. I'll do 360 and then write out DEG. Sometimes that can just see that we're for sure changing this. Okay, so alpha A, or inverse tangent of 4, was our angle in radians, multiplied by 360, divided by 2, divided by alpha pi. So yeah, we have a 75.96 degrees. So our guesses were very good. And hell yeah. And let's figure out the error on this when we do pi divided by 2. So we're going to go pi divided by 2 minus 1 divided by 4. And I'm going to store that as x and alpha x. So we're going to go alpha x minus alpha a. Make sure it's not it doesn't matter if it's negative, but then divided by, let's do this for real. So I just did these first two, and we got that as alpha x. So I'm going to take inverse tangent of 4, that's the actual number, minus x divided by inverse tangent of 4 times 100%. And we just have a 0.37% error on that. So that's really cool. And now let's pick something that's, let's pick something that's really small. So we're going to do inverse tangent of 0.25. This gives us this angle, so we're going to go times 180 divided by pi. We're using a trickier one because this is in radians, and we're going to divide by the pi radians in a 180 degree circle. So this is 14 degrees. I'm going to store that as, just know that we're dealing with a 14 degree triangle. I'm going to go back to inverse tangent of 0.25. We got 0.24497 radians. I'm going to store that as, I'm just going to leave it. So that is what we're shooting for. If we do pi divided by 2 minus 1 divided by 0.25, whoa. Oh no, that should have worked. Yeah, so with small, I was figuring that. I figured at some point with small numbers, you would get, this would be off. That's the thing about these series. Just because we threw in a very large angle at 75 degrees, and we really honed it in with a very low amount of error, like 0.3% error, doesn't mean your error is going to be the same for all of them. So this error, we're going to go, yeah, it's real bad. So let's go pi divided by 2 minus 1 divided by 0.5. So you can't even do that. Well, yeah, let's go back to our inverse tangent of 0.25. This is a 14 degree, or it's 0.24 radians. And so let's do these first three. And I'm going to do 0.25 stored as x. So we're going to go pi divided by 2 minus 1 divided by x plus 1 divided by 3x to the third. So perfect. Now we have something that's yeah, am I doing something just horrible? Oh, let's do inverse tangent of 0.25. Yeah, we're on point. X is 0.25, and wow. All right, let's go minus 1 divided by 5x to the fifth. Yeah, I think we're writing this in. So we have pi divided by 2 minus 1 divided by x plus minus, and I don't know why this equation is just Oh, you know what? This might have limitations. Let me check the book. Alright, hell yeah. Now this is going to be cool, because we're going to do a kind of a learning moment. So reading this, man, it took me a while to read this. This, even greater than and less than, you know, sometimes I don't pay attention, but even just reading this, I was just like, what? I thought it was less than, or, anyway, I thought it was -1 to 1. No, it's x has to be greater than 1 or greater than -1. So we were totally right on with 4, and probably the bigger x is, you know, the better this thing is going to converge. So this doesn't work when x is less than 60 degrees, you know, less than 57, less than 1 radian. Or a ratio. No, it doesn't work with a ratio less than 1. So a ratio of 1 is 45 degrees. Okay, perfect. So this only works, and that's going to be 0.7 radians. Or 0.75 radians. Yeah. Hell yeah. But from 45 degrees to 0, what we know is that we know this. So let's write this. This will be pretty cool. And again, I need to do this more. So we have tangent, inverse tangent is sine theta divided by cosine theta. Oh, so this is going to trip me out. Is inverse tangent theta equal to inverse sine? Oh, whoa. Oh, yeah, because if we take the inverse sine of shoot. Alright, so we have tangent of our angle is that ratio of I'm just going to do 0.5 divided by 0.866. Obviously, we're doing this 30-degree triangle. And now we're going to take the inverse tangent of the tangent of the angle. So we're going to take inverse tangent of that ratio. And that's going to give us the angle. So the angle is equal to the inverse tangent of 0.5 divided by 0.866. Cool. So how does that apply over here? What was I even trying to do? Oh yeah, I knew that tangent of this was sine theta divided by cosine theta. That is the ratio as well. So, and I want to take the inverse tan of both sides. And so isn't that just the same thing as the angle is equal to the inverse tangent? I mean inverse sine of this would be the inverse tangent of sine. Yeah, never mind. I'm mixing up some stuff. So oh no, I'm good because yeah, we just have to get a number for these. So we, yeah, this is going to be cool. So we have, I don't even know where that series, but we wrote down the series. Alright, hell yeah. So this is going to really show my understanding of how this works. Because any angle that's less than 45 degrees, you know, the ratio, let's do this. Hopefully this works. Oh man, maybe get a new sheet of paper. So if we have a 45 degree angle, tangent, inverse tangent of that number, that ratio is going to be 1. So that ratio is going to be 1, because both those are the same. If we have 30 degrees, 0.5, 0.866, ratio is going to be about 0.6. And look at this. So, and this is going to be 0.8, no, this is going to be 0.707, and this is going to be 0.707. And so this is the sine component. Hypotenuse is 1. We're going to go down to a 0.25. This one is approaching 1. And so now we just have a ratio of 0.25. And so that's the tangent. Now if we do the sine of this is 0.25. So if we do inverse sine of this angle, you know, or whatever this is, it's going to be 0.25. Inverse tangent is going to be this. So these are the same. Like 0.5 is close to 0.6. You know, 0.5 is close to 0.577. So just even right there, if the angle is less than 30 degrees, and even, it'd be kind of sloppy, but even from 45 to 30, what we're saying is inverse tangent of x is equal to sine of x. And let's do that for, we were trying to find inverse tangent of 0.25. And so it's this. Well, let's just do inverse sine of 0.25. And hell yeah, they're pretty close to the same numbers. And then so here, it's not very nice, but here is the series for inverse sine. And let's see how far we have to carry this. So we're going to go 0.25 stored as x. And we're just going to do x. Okay, hell yeah, 0.25. Okay, so inverse sine is going to be inverse tangent. So inverse tangent of 0.25. Oh, hell yeah. So just right off the bat is like you don't even need all this series. Because we were saying inverse tangent of 0.25. I mean, I should have just noticed that off the bat. But it's not until you play around with this stuff where you're just like, oh, okay, I get it. So let's see what our error is here. Because if we're just saying it's we're going to store that as alpha a. So we're going to have 0.25 minus alpha a divided by alpha a times 100%. And this is a 2% error. So just saying that inverse sine of x is and inverse tangent of x is x, it gets us pretty close. Because even inverse sine of x of 0.25, we're going to store that as alpha a. And we're going to go alpha a minus 0.25 divided by alpha a times 100%. That's even better. That's a 1% error. Okay, so sweet. And let's do it one more step. So we're going to say we got x is 0.25, so we're going to go x plus x to the third divided by 2 divided by 3. I'm going to store that as alpha a. I'm going to go inverse tangent of alpha x minus alpha a divided by inverse tangent of x times 100%. And we have a, I don't even know, maybe I did something wrong. I felt like I got more error there. Let's check this out. Inverse sine, are we always additive? Yeah, always additive on that. But yeah, we're trying to use inverse sine of x to chisel out tangent, you know. So yep. So there's no saying that this is actually going to get us closer to this because of that. So but yeah, that's pretty cool. So let's try a 45-degree triangle. So we're going to convert that to radians. So we got 45 degrees divided by 360 degrees and 2 pi radians. We're going to figure out how many radians that is. 45 divided by 360 times 2 pi. And that's going to be 0.785 radians. I'm going to store that as alpha x. And if I did inverse tangent of that, I'm just going to say that's 0.785 for a 45-degree triangle. And but yeah, let's do the ratio. If the all right. Oh, I was just about to lose my mind because we just found out that a 45-degree triangle is 0.85 radians, and a 45-degree triangle, these two sides will be the same, 0.707, and the ratio between them will be 1. So yeah, we do have quite a bit of error here. By saying that just this number in radians for a 45 is the let's see, the angle in radians is the ratio. And what that would say is it would be the opposite. If we took inverse tangent of 1, what we're saying is that, hey, this angle is small enough that we can just say this is going to be an angle of 1, but that would give us an angle of 57 degrees where a ratio of 1 is an angle of 45. So we do have quite a bit of error there. The error would be 45 plus 57. I'm sorry, 57 minus 45 divided by 45 times 100. So we would have a 26% error there. But hell yeah, so at least we know if we do 30 degrees and lower, we're pretty close. because the ratio on inverse tangent, so if we have 30, yeah, it's inverse tangent of 0.5, or 30 degrees divided by 360 times 2 pi. So this is the radians, and if we do inverse tangent, is that how you do it? Holy hell. No, tangent of, if that's the angle, if we have a 30 degree angle, 30 degrees, and I just found out that it's 0.5235 radians, then what's the ratio? You would take the tangent of that angle, 0.523 radians, and that would give you this ratio. And so we're going to take the tangent of that angle. I'm going to store that angle. And you get that ratio of 0.577. Now what we were trying to say is just like, well, okay, and that is the ratio that we're going to get. So what we were saying is that inverse tangent of this ratio, 0.577, could just be the angle, 0.577 in radians. It's not, the angle is this. So now we're going to figure out the difference between those. I'm going to store this as x because that's the ratio. Theta is the radians. I think that's the hardest thing when dealing with, even from the start. Inverse tangent of a ratio gives you an angle. Alright, so we're going to have the angle. Yeah, the angle is right on. Oh, we're taking the inverse tangent of the ratio, though. So the ratio is... Alright, let's talk through this. So we have this triangle, 0.5, and then 0.866. The tangent, the ratio of the tangent of it is 0.5 divided by 0.866. Cool. We're going to say the inverse tangent of that ratio gives us the angle. And we're just going to say the angle is 0.577. So that's what we were basically saying. It's not. We know the angle is this alpha theta. So we're going to subtract those and then divide by theta, multiply by 100%, and we get a 10% error. So using kind of that small angle thing, or just having it work out. And again, that goes back to this circle in a radian being... oh, yeah, we should go over this. The reason this works is when you do a circle with the radius, we said if you drape it up to there, that's going to be 1 radian. Now, if you drew a straight line to here, hey, this curved path is a little bit longer. But the second you get halfway is like, hey, this curved path and then a straight line. Not necessarily a straight line, I guess. I guess I'm kind of messing that up. So 60 degrees. If we went to 30, it's this. The line from here to here, which is that sine component. If this is the angle, here's the sine component. That component is basically the length of this arc length. And when we're dealing with radiuses of 1, there's no difference. So let's draw a circle again. If we have a radius of 1, this arc length up to here this is going to be, let's say it's 1 meter. This is going to be 1 radian, and this arc length is 1 meter. So this arc length, 1 meter is equal to 1 radian. Even though the units are different, that's kind of definitionally kind of what we're talking about. And so then there's kind of 3 things that we're trying to equate. We're saying, hey, if this is 1 meter up to here, maybe this is 1 meter right here. But you can see at 60 degrees, no, if this is 1 meter, this is less. This is going to be 0.866. At 60 degrees, this is going to be 0.5. It's kind of chiseled right down. But when we get to a 30 degree triangle, if that's 60, 30, 60, 90. If we get to a 30-degree triangle, this straight down distance, now we're saying this is 0.5 meters. Hey, maybe this is 0.5. And that's what we, kind of what we see. This is going to be 1, this is 0.5. Now, this isn't 0.5 radians because it's 0.52. So this is definitely 0.52 meters. So this isn't equivalent, but it's close enough that you can say those two are the same. All right, hell yeah. So I don't know if I'm going to actually do this derivative. I think we should, and probably call it a video. So let's do that. Alright, hell yeah. Because this is the first time walking through this derivative. But it's cool because we first have to look at what tangent of x is. Well, we say that if we have inverse tangent of that ratio, you know, between like a number between 0 and 1, or cosine of that ratio, hey, we're going to pop out an angle. Sweet. Same thing with inverse tangent of that ratio. This is just a percentage of hypotenuse. You know, I mean, that's why I wrote it like that, because that's always going to be the percentage of the hypotenuse. This ratio is going to be all over the place, from 0 to infinity, actually negative infinity to positive infinity. Okay, but still you're going to pop out an angle. So we can say that inverse tangent of x is theta, and I'm sure you would want to write it like this. Theta is equal to inverse tangent of x. And that's just the wild thing. The wild thing about this, you know, when you just see on the internet some sort of equation and then a differential, is just like, well, it's no different than saying, hey, what's the derivative dx, let's write it the same, of x squared? You know, again, you're like, well, what is x squared? Well, sometimes we say like y is equal to x squared. And then for whatever reason, that just kind of looks like the form that we wanted in. And you're just like, oh yeah, that's what I'm familiar with. You know, this equation that, hey, y is equal to x squared. You know, if we set y is equal to 0, we can figure out where that thing crosses the y-axis. This is the y-axis, x-axis, or what? Oh yeah, where, like, if this is like 1 and this is negative 1, but this is 0, where does this function cross this line? You know, on the y-axis. Yeah, it's kind of like longitude and latitude. It could be over here, but that could be the solution. But anyway, it's going to be like right there as we do that one. I don't know, yeah, I'm just getting at like, hell yeah. Like, whatever this is, it's probably equal to something. And so that was kind of the first step in this equation. The second thing, if you're taking the derivative of this side, well, this as well. Aren't you taking the derivative of both? So even like right here, taking just the derivative of x squared, yeah, we're just like, okay, I can do that. That's just going to be 2x. But that's so bizarre to me that we're going to take x squared, turn it into y is equal to x squared, and then take the derivative of both sides, still with respect to x. So then it's going to look like this. It's going to be derivative of y dx is equal to derivative dx x squared. All right, hell yeah. And sometimes it's useful to put these in brackets. I don't know, just so you can kind of see that. But yeah, so we have dy dx, and I guess that's just synonymous with just everything that's what we know as the differential equation of of what we're trying to do. And so now we have differential of x squared with respect to x, and sweet. And so sometimes, hey, we just want that, and we just want to know that that's equal to 2x, and then life goes on. Okay, so back to this one. Yeah, we just take the, we differentiate both sides. It's just like, but yeah, that was the second part of this where I just, I never knew that. One, just like, hey, this is equal to something. That was kind of step one. Two is that you can obviously differentiate both sides. So we're going to go d theta dx is equal to d inverse tangent x dx. Okay, hell yeah. But from here, Oh, and we don't even want to do this. That's not even the way they do it. We're kind of in the same boat. I mean, this is that problem. This is the initial problem, and so fresh sheet of paper. So we have theta is equal to inverse tangent of x. But we just spent this entire video being like, whoa, yeah, we can say that tangent of theta is x, just by putting the inverse tangent on this side, and then no, I'm sorry. If we're trying to get rid of this inverse tangent, we're taking the tangent on this side and then the tangent on that side. All right, booyah. Okay, and now we can just say, hey, cool. Now we're just going to, yeah, and maybe that's synonymous with, hey, if we have the derivative of dx x squared, this is just kind of on the fly, we're going to say, hey, that's going to be y is equal to x squared, take the derivative. But instead, we took the derivative both sides, but maybe you want to do something funny and just do like, hey, I want to go y divided by x is equal to x, and now I'm going to take the derivative of that. So I'm going to take the derivative of y divided by x dx, and is equal to derivative of x dx. And cool. But yeah, obviously you might run into some issues here. This one you can do. Alright, so over here, kind of the same thing. We're going to differentiate both sides with respect to x. Tangent theta is equal to derivative with respect to x of x. Alright, so this is why you should do as much differentiating as you can, because then you can see the pitfalls. Like, hey, this should just be like big alarm bells going off that you don't have x here. That's like saying, hey, I want to take the derivative of x squared with respect to y. You know what I mean? Well, you don't have y. You have x squared. So like what gives? Yeah. So it's kind of the same thing here, but you use the chain rule. You can take the derivative with respect to theta. So you're basically saying, hey, derivative of this function, theta, and we're trying to take it with respect to x. We can't do that, but we can do this. Derivative of the function theta with respect to theta multiplied by the derivative of x, derivative of theta with respect to x. Because now these two things, like, it's kind of the equivalent of like, hey, can we just multiply by 1? Just multiply by a ratio that's kind of equivalent to 1, and that's kind of what we're doing. And that's the whole premise of the chain rule, because we can differentiate with respect to this theta. And I guess the take-home point is we do this because we have charts in our books that say, hey, we know what the derivative of that, we know we can put an equation, and our calculators are set up to take that equation and be like, booyah. Alright, so this becomes the derivative of tangent theta with respect to theta, and then multiplied by the derivative of theta with respect to x. This is the same over here, and we can even just do this one at this point. Derivative of x with respect to x is just 1. Alright, hell yeah. And then we go back to, writing this. This is angle is equal to d dx inverse tangent of x. And maybe we didn't want to do that. Oh, no. This is, sorry. Tangent of x, or this is the angle. The angle is equal to inverse tangent of x. So the derivative of this angle with respect to x is equal to the derivative of inverse tangent with respect to x. Cool. And we can see that these two things are the same. And then right here we can see that, oh, we have that thing, is this thing. So if we solve for this thing, we do get that. Hell yeah. Alright, I feel like I'm totally messing this up, but let's just carry on. So right now we're going to be doing this derivative. And yeah, this is a cool one. Turn tangent into sine theta cosine theta, and then take the derivative of it. And so we use the quotient rule. Made a video on that. It's bottom d top minus top d bottom, all divided by the bottom squared. I mean, it's hella tricky, but it's no different than oh, and this is yeah, we'll have to do it this way. But so sweet. And it's fairly fast. I'll go over the fast way. So bottom d top, that's going to be cosine. We're going to write cosine right here. And then the derivative of sine is cosine. So we're going to have two of them. And then we're going to go minus top d bottom. So we're going to have sine theta. But derivative of cosine is negative sine. Sweet. So we're going to have two of them. This becomes 1, all divided by the bottom squared, cosine squared theta. So we have 1 divided by cosine squared theta. I'm going to write that in. And I'm going to keep it like that. So I'm going to have 1 divided by cosine squared theta. D theta dx is equal to 1. And man, I feel like I've already messed up something. But anyway, I'm just going to take this to over here. And now we just have to figure out oh man, I probably really messed this up. But this is where you use that identity. But I think I already messed it up. So we're going to take this and divide by a cosine squared theta on both sides. Oh yeah, maybe I shouldn't have brought it over here. So there you go. No, we're good. But yeah, this just trips me out. So the whole premise of this is that, hey, we do have what we want. You know, we already said, hey, we got what we want. It's just in terms of 1 and inverse cosine squared of theta, and we don't want it in terms of theta. We need this thing in terms of x. But hey, we know that x is equal to tangent theta, so we're trying to do anything to get this into something is equal to tangent theta, and we're going to get a tangent squared theta. So let's maybe just use a sheet of paper, but we're going to divide this by cosine squared theta. So if we do that, sine squared theta divided by cosine squared theta is that tangent squared theta. This is going to be plus 1 is equal to 1 divided by cosine squared theta. Sweet, and I have this 1 divided by cosine squared theta. Booyah. So I'm going to put this in over here. I'm going to do this all just in one step, because we know this is what we want. This literally is the derivative of inverse tangent x dx. So we're going to have this 1, and we're going to divide it by whatever this was. That is this, and so I'm going to write it just in a different way. I mean, typically they write it like 1 plus x squared, but you can see that now tangent squared of x, we have this. And so we're going to say that's 1 divided by x squared plus 1. So hell yeah. So we have our solution to this problem. And brutal. You can do the same thing for inverse cosine. Same process. You're going to get to where you're going to take the derivative of a cotangent, which is just this flipped upside down, and it's going to be bottom d top minus top d bottom divided by the bottom squared. You're probably going to get 1 over cosecant squared theta. Yeah, probably, because you're going to get negative 1 divided by, because of the sign changes, that you are going to get a 1, but you're going to factor out a negative 1 to do that. And then then you got to do that one that we did. You're going to divide this by sine squared theta, so we can even talk through that. If you divide this by sine squared, you're going to get a 1 here. You're going to get a cotangent squared theta, and then 1 divided by, sine squared theta. So this is going to be your 1 divided by sine squared theta. When you do that, it's going to be a negative, so we got to carry that negative through. And then booyah. That is going to equal 1 divided by the cosecant. That's going to be this side is equal to whatever we had over here, which was going to be cotangent. Yeah, we're dividing this by sine. 1 plus cotangent. So you're going to have negative, and then you're going to put this over there. So you're 1 divided by cotangent squared theta, and then you would have right here cotangent theta is equal to x, and then you would have negative 1 divided by x squared plus 1. Holy hell. But yeah, that's just kind of, that'll be for a separate video. I'm just glad I could talk through that. That probably made no sense. But I don't know. I think this is what people want. I'm not very good at this. Is just kind of the first time, like, talking about trigonometry that's right at my limit. But I'm going to talk about things that other people aren't going to talk about. I'm going to try to, oh yeah, we definitely have to finish with being like, what the hell is the derivative even mean? So, and could we have figured that? Because we got this answer, but we definitely need to double check it. Alright, so booyah. This is probably the funnest part for me. Alright, hell yeah. Hopefully like the last 5 minutes. So we know that this is equal to 1 over 1 plus x squared. We know that x is, and what does this give us? This gives us the change in the angle, because tangent, inverse tangent of x gives us the angle. The derivative of it gives us the change in the angle with respect to x. So whatever number is over here, so this is going to be 1 divided by 1 plus x squared. So now we're just going to see if this actually checks out. And so I'm going to draw my triangles. So we're going to do a 30. I'm just going to say it's 0.5 radians. What do we need? We need the ratio. That's going to be 0.5 divided by 0.86. We're just going to say a ratio of 0.6. We're going to draw 45. Ratio of 1. This is going to be 0.75 radians. We're going to draw a 1. Radian of 1. It's about 60 degrees. And we're going to have 0.866. We're going to have 1.7 ratio. I'm going to go down to 0.25. We have a 0.25 radians. And we have a ratio of 0.25. Alright, hell yeah. And then I'm even going to go up to a, yeah, we're going to do all these. It's going to be really fun. We're going to go, oh, sorry, this is a radian of 1. Yeah, maybe we're done. Okay, hell yeah. So, the change in the angle, we're going to change our angle by 0.25. 0.25 to 0.5 is a change of 0.25. That's our angle change. Now how about our ratio change? Our ratio change, 0.6 minus 0.25. Our ratio changed by 0.35. So this number, 0.25 divided by 0.35, should be 0.714. So that's kind of what we're shooting for. And let's try it out. So, but because this change was in between 0.25 and 0.5, like literally the angle had to have been kind of in the middle. So, 0.25 plus 0.5 divided by 2. So this is going to be a radian. This is going to be an angle of 0.375. So that is the triangle. So if we say, hey, at oh, this is interesting. No, we got to do it the opposite way. We have to say at a ratio of in between these, 0.25 plus 0.6 divided by 2. So at a ratio of 0.425, we're going to throw it into our calculator, and then we should get this to be, what did we say? Now I forgot. Yeah, this is the angle in between 0.375. That's good. Anyway, let's do it. So we're going to do, I don't even know anymore. 0.25 plus 0.6 divided by 2 stored as x. So this is the ratio. This is right in between. We're going to put that ratio in. So 1 divided by 1 plus x squared. And we get 0.847. And that's the actual answer. And this is what we got. Okay, so, you know, fairly close. And the only reason why this isn't 100% close is because, you know, these angles are pretty far apart. 30 to, anyway. So let's do another one. These ratios go from, so the angle changes by 0.25. The ratio changes by 0.4. 0.25 divided by 0.4. And it's just real loose guessing, too. These aren't even accurate. And then what would be the middle? 0.6. Alright, hell yeah. So my camera cut out. But anyway, what we're doing is basically, we're just as it says. Like, how do you read this? It says, hey, change as the inverse tangent of x changes. And we already know, we already said this was the angle. So you're saying, okay, as the angle changes, and we divide that by the change in the ratio, that gives us a number. And for whatever reason, that number is going to be useful when, you know, using as a derivative. And that's as much as I can say on that. You know, sometimes it's like hard to get any concrete idea of what's going on. But I swear, I never even focused on like, hey, what does this say? It says we're changing this, we're changing the angle, and then dividing it by the amount that the ratio changed. We're getting a number, and for whatever reason, that number is going to be useful for something else we're doing. Okay, so what we were doing was, oh, this is interesting, because I have bipolar, and sometimes I'll get kind of hallucinations of smell. And so, I don't know, yeah, it's just, this very, I'm just going to point that out every once in a while. But yeah, sometimes when I get kind of going, okay, hell yeah. So we changed the angle, what are we doing? We changed the angle in this one, and we changed the angle by 0.25. We changed the ratio by 0.4, and we got 0.625. Cool. Now, when we put in this ratio right here, it can't be this, it can't be 0.6 or 0.1, it has to be in between. That's the whole point of, like, you know, that might be for a separate video, but hell yeah. So we're going to do a ratio of 0.8 because we did the change over here. So we didn't start here, we didn't finish here. We're kind of representing the average, which hopefully is in the middle. Hopefully it's kind of a linear relationship between these two. That's where if we get angles that are really close, you'll just be spot on. So we're going to take this 0.8, that's going to be the ratio of the angle right in between, and let's do it. So we're going to have 1 divided by 1 plus 0.8 squared, and we're going to get 0.60, like 0.610. Hell yeah, and I would say that's close enough to 0.625. You know, it's just even in the ballpark. So this is stuff that you can actually do, I don't know, to get kind of a visual representation of what you're doing. And if you just want to get a value at that point, like, you can just do it. You know, you don't have to, you know, derive a funky equation. Alright, so hell yeah, I think I'm going to be done with this, but we did a lot, so thanks for joining me, and guess what? That's a video.